Okay, so we have finished what we're going to do of trig for the year. Yay. We are moving into the unit that most kids, find the most useful and the most engaging. We're getting into the financial unit in the 3M math class. And so, were we in class, we'd spend obviously more time on this, but I'm hoping to invest as much time in here as we can and make it useful. But to begin with, what we need to do is we need to revisit some of the exponent rules that we haven't probably been all that explicit about since you have been in grade 9. So we are going to talk about exponent rules. Okay, so exponent rules. I hope everyone is doing well. Okay, so let's recall there are 3 main exponent rules that you will have learned in grade 9 that we want to revisit. We could do an exploration, but because this is review, I'm just going to go ahead and I'm going to state them. So the first one is, and I'm going to write an example and then I'll summarize it. If we had maybe not a to the m, that will make you sad. How about if we did a cubed times a to the 5th? What would that equal? Just pause yourself and think about what it is and write down your answer. Hopefully you recall that it is a to the 8th. And this is the product rule, right, of product rule of powers is what it's often called. And so it states that when multiplying powers with the same base, we leave the base unchanged and we add the exponents. Okay, so important thing is we leave the base unchanged, right? That's a big deal. And then add the exponents is the other big piece of this. Now, you might wonder, why isn't it like a to the 15th? Or, and so an easy way to kind of persuade yourself that this is right, I should have chosen smaller exponents. You could say, well, a cubed, we know that a cubed is a times a times a, right? We know that. We know that a cubed is a times a times a. And a to the 5th is a times a times a times a times a, right? That's a to the 5th. Well, if you go through and you count those up, we've got 1, 2, 3, 4, 5, 6, 7, 8, which of course makes a to the 8th. So that's an easy way to remind yourself if you don't really remember what the rule is. So there's one. So that's a big one. Imagine that we had it the other way around. Imagine we had a to the 5th divided by a cubed. What would that equal? Hopefully you remember right off the bat, you know exactly what it is. And of course, hopefully we know that it is a squared. Okay, and so this is the quotient rule of powers. Okay, and what we're going to get here is when dividing powers with the same base. So when dividing powers with the same base, we leave the base unchanged and subtract the exponents. Okay, and so we subtract the exponents, excuse me. And, as a justification for why that maybe makes sense, we could do a times a times a times a times a. So there's a to the 5th up top over a times a times a in the denominator. And we can do some cancellations. We can say, well, that one goes with that one, that one goes with that one, that one goes with that one. What are we left with? Well, there are 1, 2 of them. So it's, of course, a squared. So there's a pretty easy justification. And then finally, imagine that we had a to the 5th cubed. Okay, what does that equal, right? Well, I'm guessing by process of elimination, you can probably figure that out. But in the event that you can't, it is, of course, a to the 15th. Well, what did I do there? Well, I multiplied them. So this is a power to an exponent. Okay, and when we have that, we again leave the base unchanged. So notice a common theme here. We leave the base unchanged and we multiply the exponents. Okay, and a justification for why that makes sense is, well, here we have this thing cubed. So if I have a thing cubed, I take the thing and multiply by itself 3 times. So we're going to have a to the 5th times a to the 5th times a to the 5th. And so we've got 1, 2, 3 of those. And if we look back to the earlier rule, right, this rule up here, so you're multiplying powers with the same base, you add the exponents. Well, here we are, we're multiplying powers with the same base, right? So there's an a, an a, and an a. So we're going to add the exponents. So 5 plus 5 plus 5 is 15, right? So we have a to the 15th. And the shortcut for doing repetitive addition is multiplication, right? So that's all review. This should not come as a shock to anybody. We've done that we reviewed it in grade 9, although you should have had some exposure to it in grade 8. And then you will have made some use of it in grade 10. Well, we're back to it again in grade 11. And if you continue on to grade 12, you're going to play with it there as well. Right. So that's review. Now let's move on to some, depending on who you had in grade 9 or 10, you may not have seen some of these other rules that are quite important that we need to know. So imagine that we did, and let's take it into the realm of numbers. So just recall, and I guess I'll do let's talk some lingo here. So if I had 4 cubed, okay, so 4 cubed, this whole thing is called, that whole thing there is called a power, right? That whole thing is a power. Let's grab a different color, this color here. This thing here is, of course, the exponent, right? That's not news to anybody. That's the exponent. And this color here, this fella here, well, it is known as the base of the power, right? So that's all well and good. So, that's kind of a discussion of the language. Now, if I asked you to read that out, almost everyone would say 4 to the power of 3. And I'm sure probably you've maybe even heard me say that, although I'm pretty careful to not say it like that. Strictly speaking, we should really say this is 4 to the exponent 3, because the whole thing is a power and this is the exponent. And you might ask, like, what's the difference? Well, the difference is when I'm multiplying powers with the same base, I add the exponents. Well, when I'm multiplying the whole power, I'm not multiplying just the exponent, right? So, it's important to know the distinction. Now, we're going to talk about some different forms. This form here, the classic form, this is known as the exponential form, right? Not surprisingly, because of course it's got the exponent. That's the exponential form. And then we could move that along and we could say, well, another way we could write this exact same thing is 4 times 4 times 4. And this, well, it's called the expanded form, okay? Expanded form, because of course I have expanded it. And then we could take that and we could actually simplify that. We could figure out what that was. We could either do that in our head or we could get our calculator, we could do whatever. 4 times 4 is 16, times 4 is 64. So 64. So this one here is called the evaluated form, because we've actually evaluated what it is. So that's the evaluated form. Some people might say simplified, but we have to be careful. Simplified is not as good a description as saying it is the evaluated form. Okay, so those are all different forms, and there's going to be times where I'm going to ask you to write as, so here's where you have to be careful. I might say, take this expression and write it as a simplified exponential form. So an example of that. So if I had 3 to the 7th times 3 to the 3, let's say, and I gave you a question and I said, write your answer as a simplified exponential form. Well, what I'd want there is I'd want the simplified form with the fewest number of terms. Well, multiplying powers with the same base, we add the exponents, so that would be 3 to the 10. So that is what I would be after right there. So that's the simplified exponential form. It's as few different pieces to it as I possibly can, but it's still in an exponential form. Okay, so that's what that one would be. That's the simplified exponential form. If I had have asked for it in the evaluated form, I don't know what that is. I can't do it in my head. 3 times 3 times 3, it's a big number. But, so we have to be careful. So simplified, yeah, but if I want you to write it, like this, I'm going to say in evaluated form. Okay. All right. So that's just some lingo. Now let's look at some of those other exponent rules. So without using your calculator, I would like you to surmise, what do you think 4 to the exponent 0 would evaluate to? Okay. What would this evaluate to? Well, to the exponent 0, like what does that even mean? Well, if you type it in your calculator, you're going to see that the answer is 1. Okay, and you're like, what? So let's try it. Maybe that's just coincidence. Let's try another one. If we did 7 to the exponent 0, well, it comes out to be 1 as well. And if we did negative 15 to the exponent 0, it's going to come out to be, well, 1 as well. And it's, here you are, you're thinking, well, why on earth is that the case? I'm going to write the rule. And so the rule is going to be anything to the exponent 0 evaluates to 1. Now, what's kind of interesting is there's a bit of a caveat, like a bit of a an exception to this rule. If you take your calculator and you type 0 to the exponent 0 and you try and type it in, it actually will normally give you a math error. So you don't need to worry about this. This is extra. I don't want you to even worry about it. But it's interesting to know that 0 to the exponent 0 normally gives a math error. Normally, and you say, normally, what do you even mean? Well, it's weird. This is one of the very, very few cases in mathematics where the answer is, it's like has an ambiguity to it. And it depends on the field of mathematics you're using. If you type 0 to the exponent 0 into Google, because Google is a calculator as well, it will actually tell you that it's 1. So it depends on the field of mathematics. It's way, way beyond our pay grade to worry about it, but I just want you to be aware of that. But this is what we're going to consider right here. Is basically anything to the exponent 0 is 1. And you might think, well, how does that make any sense whatsoever? Well, I'm going to offer you a bit of a proof using the stuff that we just worked with to try and figure out what it is. Here's the question I have for you. Anything divided by itself. What's anything divided by itself? What's 6 divided by 6? Hopefully you say, well, it's 1. Okay, so now let's look. You know that anything divided by itself is 1. So if I said, well, 2 cubed divided by 2 cubed, you know that anything divided by itself is 1, right? We know that from prior knowledge. We know this. We know this. Now, let's look at if we just did this with the exponent rules that we just had. The exponent rules say when we're dividing powers with the same base, the base remains unchanged, and we subtract the exponents. Well, the base remains unchanged, so that's 2, and 3 minus 3, because we subtract the exponents, is 0. So one thing from prior knowledge tells me that 2 over 3 divided 2 to the third divided by 2 to the third is 1. Some new math tells me, no, it's 2 to the 0. Well, so I'm going to put, we learned this. What we know, however, is that these two things must actually be the same. So 2 to the exponent 0 is 1, right? So there we go. So anything to the exponent 0 works as 1. And that kind of goes to why 0 to the 0 doesn't work, because if I did 0 to the 5th divided by 0 to the 5th, well, that'd be 0 to the 0. But when I divide by 0, the world blows up. So that's kind of the why we would get a math error. Why we wouldn't get a math error and we'd sometimes get 1 is simply for consistency and saying that everything to the exponent 0 evaluates to 1. And there are some fields of mathematics where that's important. Okay. okay? But we're just going to go with anything to the exponent 0 evaluates to 1. I'm running out of room, goodness. All right, so on we go. So imagine now that we are going to continue. So here comes, not imagine, we are going to continue. So how about if we had, let's say, a negative exponent? So what the heck, negative exponent? So imagine that we had, how about 3 to the exponent negative 2? It's like, that's a weird one. I'm going to tell you, if you type that into your calculator, 3 to the exponent negative 2, I should have used a nicer number. That would be 0.1 repeated. Yeah, that'd be 0.1 repeated. And it's like, where did that come from? This kind of looks like a pie. I'm going to make these ones obvious. And so you're like, I don't know where that comes from. Well, I'll write it in another form. It's also 1/9. Like, oh, okay, I still don't see where it comes from. How about if we had 5 to the negative 2? Well, 5 to the negative 2, well, it would be in fractional form, it would be 1/25. You're like, what? How about 2 to the negative 3? Well, that would be 1/8. So here's what's actually going on, is when we have a negative exponent, it causes the base to flip over and reciprocate. Okay, so make it more obvious. If I had 3/2 to the negative 2, the negative would cause this whole thing to flip over. So it would be 2/3. That gets rid of the negative and it's still squared, right? There's still squared. And then we're going to have 2 squared and 3 squared. So it would be 2 squared over 3 squared, which would be 4/9. It's like, oh, okay, so that negative causes a reciprocal to happen. So where this one came from is really, this is over 1, right? And so if I flip that over, it's going to be 1/3 to the, get rid of the negative now because I flipped it, 2. Well, 1 squared over 3 squared is 1/9. Similarly here, this would be 5/1. So then it would become 1/5 to the 2, which is 1 squared, which is 1/5 squared, which is 25. Down here, this would be 2/1. So if I flip it over, it becomes 1/2 cubed. Well, 1 cubed is 1, 2 cubed is 8. And that's where it came from, okay? So when we have a negative exponent, it causes the base to flip, or the proper math term is reciprocate, okay? So a negative exponent causes the base of the power, this is why we need to use all the right words, to, I'm going to use the big word, reciprocate, which just means flip. Okay, and that's what a negative exponent does. That's all it does. Everything else stays the same, right? So there we go. I'm going to extend this page so I've got a little bit more room to play with here. So File, resize this. I don't want to keep the ratios. Let's make this 8,000 so we got lots of room. Okay, so dang, that didn't really work the way I wanted it to. Where did it go? Interesting. What the heck? All right, well, I'm going to save it and then create a new one. So File, save as, make it a JPEG, and this is MCF3M, and this is exponents, done. Save that, and then File, new. Okay, sorry, apologies. All right, so we're almost there. There's only one other exponent rule that we need to worry about, and that is going to be a rational exponent. Rational exponent. We can go with even a bigger rational, but we're only going to go to the exponent of 1/2. So the exponent of 1/2. What exactly does that mean? Exponent of 1/2. So imagine that we had, I don't know, 36 to the exponent 1/2. Type that into your calculator. Now, if you know how to type in your calculator, you'll need to type it in with brackets. So you do 32 or 36, excuse me, to the exponent or whatever exponent button you have. And then you need to put it in brackets, 1 divided by 2, Or in theory, you could have typed 36 to the exponent 0.5, right? That would work as well. And what do you get? Well, hopefully, if you typed it right, you get 6. And what? So how about if we did 100 to the exponent 1/2? Well, it's going to come back as 10. How about 49 to the exponent 1/2? Well, that's 7. How about 64? Hopefully, you're seeing what's going on here. This is 8. We'll do one more. If we had 81 to the 1/2, I'm hoping that you're saying to yourself, well, that's going to be 9. So the exponent of 1/2, okay, the exponent of 1/2 is the square root of the number. It's the square root of the base of the power. And again, you might question why that is. Well, I can give you a quick demonstration. So if we said, what is the square root of, go a nice number, it's 25, and you're like, well, it's 5. Okay. So if I wrote, what is the square root of 25 times the square root of 25? And you think, well, square root of 25 times the square root of 25 is, well, it would get rid of the root, right? So the root of 25 times the root of 25 is going to be, well, it's 25. Well, this is two matching numbers that multiplied to give me this. That's what square root is, right? It's the two matching numbers that multiply together to give you the whole. Well, this is 25 to the exponent 1, because hopefully you remember, I should have iterated this at the beginning, is that when we have a power that doesn't have an exponent listed, we know the exponent is 1. So this is two numbers that are identical that multiply to 25 to the 1. So look what we can do. 25 to the 1/2 times 25 to the 1/2 is equal to 25 to the 1. And why does that make sense? Well, when we multiply powers with the same base, we add the exponents. 1/2 plus 1/2 is 1. Okay, so the base has stayed the same, and we have an exponent of 1. So this means two matching numbers that multiply to be 25. Well, you know, and I know that those two matching numbers have to be 5. So that means that what we've got is to the exponent 1/2 is the equivalent of square rooting. And you've probably seen me on the calculator, the graphing calculator up on the smartboard, when I go to do square root. Like if I had an answer that was like 72.3 and it was sitting there as an answer, I actually never use the square root button. I always say to the exponent 0.5. It's just faster, right? So to the 1/2 is a square root. Okay, so those are the rules. Now we can do other exponents that are rational exponents. So if I had, I don't know, like 81 to the 3/2, the rational exponent doesn't have to just be 1/2, but that's sort of beyond what we have in this curriculum. I can show you what it would be, but I'm not going to ever test you on that. So what we could do is we could rewrite this. We could say, well, this is equal to 81 to the 1/2 to the 3, because when we have a power to an exponent, we multiply the exponents. So then we'd say, oh, well, that means that this is 81 square rooted, which is 9, and then we have 9 cubed. So 81 times 9 is 279, I guess. Is that right? I think so. Yeah, so 279 is what that would be, I think, but I could be mistaken. Right, so the idea is that the top of the fraction is going to be the power, and the bottom of the fraction is going to be the root. But we don't need to know that. We just need to know that anything to the 1/2 is the same as square rooting. So we can put some of these things together, right? So let's consider some questions where we put stuff together. So if I said to express as a simplified power, or I would like it in simplified exponential form, right? So simplified exponential form, what that's going to do is I want you to express it as a power. And then I might also say then evaluate, right? Which means you would write what the, quote unquote answer is, okay? So let's look at a couple of simple examples. So imagine we had 3 to the 4th times 3 cubed divided by 3 to the 5th. And I want you to express that as a simplified power to begin with. Well, what we're going to need to do is we're going to have to fully simplify the numerator. And if there was more stuff going on, we need to fully simplify the denominator before we do any division. So here we go. We're going to have multiply powers with the same base. Here's my same base. We need to add the exponents. So this would be 3 to the 7th, and I'm going to leave the denominator alone for now. So that's 3 to the 7th divided by 3 to the 5th. Well, when we divide powers with the same base, we subtract the exponents. So that would be 3 to the exponent 2. So there it is, expressed as a simplified power or simplified exponential form. If we then had to evaluate, well, 3 squared is 9. So those are the answers, right? This is the simplified exponential form or the simplified power, and this is the evaluated form. Okay, I could have also asked for the expanded form in theory, although it would be rare I would ever do that. The expanded form would simply be 3 times 3. Okay, so let's try another one. Let's try one that's a little bit more challenging. How about if we had 3ab squared cubed times 3 squared a squared b to the 4th to the 5th. Looks pretty challenging. First thing I want to reiterate, if a power is shown, but it doesn't have an exponent, okay? So this a doesn't have an exponent on it. Well, yes, it does. The exponent is 1. Same goes for the 3. The 3 has an exponent on it as well. It's not shown. It is 1. Anytime that we have a power without an exponent showing, the exponent is 1 and not 0, right? Because if it was 0, 3 to the 0 is 1, and we just get rid of it. And a to the 0 is 1, and we just get rid of it, right? So if there is a power without an exponent showing, we need to put in a 1. So that's the first thing I want to point out. Then what we're going to do is we have a power to an exponent. How do we simplify that? Well, we simplify that by multiplying. So this is going to be 3 cubed because 1 times 3 is 3, and a cubed because 1 times 3 is still 3, and then b to the 6th because 2 times 3 is 6. So that's b to the 6th. Same thing over here. So times 3 squared to the 5th. Well, 2 times 5 is 10. So this would be 3 to the 10th. 2 times 5 is still 10. So a to the 10th. 4 times 5 is 20. So b to the 20th. Okay. And so then what we're going to have, we're going to multiply powers with the same base. Now, there's a bunch of different bases here. You can't just say, oh, I'm just going to add all these things up. You can't do that. We have to have the same base. So here's a base of 3, and here's a base of 3. So when we multiply powers with the same base, we add the exponents. So this becomes 3 to the exponent 13. And a, well, a is also going to be to the exponent 13. And b is 6 plus 20, so b to the 26th. And there it is, okay? And so that is, kind of, I know it doesn't seem like the basics, but it actually is some of the basics for exponent rules. So I'm going to leave it there, and I'm going to get you some homework questions to play with as well that I'll put up on Google Classroom. But for now, that's where we're at. We're going to continue on with this next week, and we're going to bring in some of the financial aspects. It's going to rely on this exponential and exponent knowledge. Okay, sounds good. Have a lovely remainder to the week.